What if everything we thought we knew about the universe was wrong? NASA's most powerful telescope just found something so impossible that scientists are desperately trying to explain it away. And the more they look, the more they realize we might have been fundamentally mistaken about how the universe actually works. This is not speculation. This is not theory. This is happening right now in observatories across the globe, and the discovery is forcing astronomers to question the very foundation of modern cosmology. In December 2021, humanity launched its most ambitious scientific instrument into the darkness of space. The James Webb Space Telescope, or JWST as scientists call it, was positioned at a special location called the L2 Lagrange point, nearly 1 million miles from Earth, with its massive 6.5-meter mirror and infrared capabilities far beyond anything we had ever built. This telescope was designed to peer back through time itself to see the earliest galaxies ever formed. But what it found has shattered the careful models that physicists have spent decades constructing. For generations, cosmologists have operated under a fundamental understanding. The Big Bang happened approximately 13.8 billion years ago. In the immediate aftermath, the universe was nothing but hot plasma and radiation. Gradually, this plasma cooled. Hydrogen and helium atoms formed. These atoms clumped together under gravity, and after hundreds of millions of years, the first stars ignited. These stars fused hydrogen into heavier elements. When they exploded as supernovae, they scattered these heavy elements into space. This material formed new stars and planets. Eventually, galaxies assembled themselves into vast structures held together by gravity. This process, according to our models, should have taken billions of years to produce the large, complex galaxies we see today. But something is catastrophically wrong with this timeline, and the James Webb Space Telescope has the evidence to prove it. In 2025, astronomers using JWST identified something that should not exist. They found a galaxy designated JWST Z14-0 at a redshift of 1432. To understand what this means, you need to understand that redshift measures how far away a galaxy is and how long its light has been traveling to reach us. A higher redshift means we are looking further back in time. This particular galaxy's redshift places it approximately 290 million years after the Big Bang. Think about that number for a moment. 290 million years. That is the amount of time this galaxy had to form and mature into the massive, structured, fully developed system that the telescope observed. But here is where it gets truly disturbing. According to everything we know about physics and stellar evolution, this simply is not possible. For a galaxy to exist at this point in cosmic history, vast amounts of gas must have collapsed, compressed, and ignited into stars. These stars must have lived their entire lives and exploded, scattering their heavy elements across space. The new stars must have formed from this enriched material. And all of this must have happened in less time than it takes to complete a single orbit around our galaxy. The numbers do not add up. They cannot add up according to our current understanding of physics. Yet the data is undeniable. The telescope has captured the light from this ancient galaxy. The measurements have been verified and peer-reviewed. This galaxy absolutely should not be there, and yet it is. But JWST Z14-0 is not alone. Just when scientists thought they might have found an anomaly, a one-off quirk in their data, JWST broke its own record. In January 2026, astronomers announced the discovery of an even more distant galaxy, this one designated MOEM-Z14. This galaxy has a redshift of 14.44 and emitted its light just 280 million years after the Big Bang. It is even older than the previous record holder. It is even more impossible. The team of researchers, led by astronomers at MIT's Kavli Institute for Astrophysics and Space Research, described this discovery as both challenging and exciting, but the underlying tone was one of bewilderment. How could this be happening? How could galaxies of this scale and complexity have formed so early in cosmic history? And then came the cascade of discoveries that truly terrified the scientific community. Researchers identified not one or two problematic galaxies, but 300. 300 galaxies that are brighter than they should be according to current models. 300 objects whose existence contradicts the theoretical frameworks that have guided cosmology for decades. The implications are staggering. These are not marginal errors in observation or measurement. These discoveries are not borderline cases that might go away with better instruments. These are fundamental contradictions between observation and theory that cannot be ignored or explained away by minor adjustments to existing models. When astronomers gathered to discuss these findings, the response was one of shock and confusion. Conferences that had been planned for discussion of incremental findings suddenly became forums for existential questioning. How could this happen? How could our most powerful telescope reveal that our most fundamental understanding of cosmic evolution was wrong? The crisis in confidence spread through universities and research institutions worldwide. Researchers who had built entire careers on models that now seemed inadequate found themselves questioning everything they had built. Some scientists proposed that early star formation was dramatically more efficient than previously calculated. Perhaps the earliest stars formed much faster than we thought possible. Perhaps they converted their fuel into new stars at an unprecedented rate. Under this model, the universe's star-forming machinery might have been operating at peak efficiency when we thought it was still warming up. If this is true, then our estimates of stellar lifespans, supernova rates, and elemental abundance might all need significant revision. Others suggested something even more radical. Perhaps dark matter, the invisible substance that makes up most of the universe's mass, was behaving in ways we do not fully understand. Perhaps dark matter interactions in the early universe were creating gravitational environments that allowed structures to form much faster than gravity alone could accomplish. Dark matter comprises roughly 85% of all matter in the universe, yet we have never directly detected a single dark matter particle. We know it exists only through its gravitational effects. Perhaps our models of how dark matter behaves in the extreme densities of the early universe are profoundly incomplete. But a smaller, more vocal group of scientists was proposing something far more troubling. Perhaps the standard timeline itself is wrong. Perhaps the universe is not 13.8 billion years old in the way we currently calculate it. Perhaps there is something fundamentally broken about our understanding of cosmic chronology. These researchers pointed out that our age estimate comes from observing distant supernovae and measuring how the expansion of the universe has accelerated over time. If something is wrong with those measurements, or if the physics governing cosmic expansion is more complex than we assume, then everything changes. The discovery did not stop with these ancient galaxies. JWST continued to reveal objects that defied explanation, one after another in rapid succession. Astronomers found massive barred spiral galaxies existing just 2 billion years after the Big Bang. Barred spiral galaxies are extraordinarily complex structures. The bar itself is a dense concentration of stars that forms through billions of years of gravitational interactions between different parts of the galaxy. It is an architectural feature that takes immense time to develop. Yet here was evidence that these structures were forming when the universe was less than 15% of its current age. The galaxy designated Cosmos 70706 appears to have existed approximately 11.5 billion years ago, meaning bars were developing just 2 billion years after the Big Bang. Then there was the discovery of a giant galaxy that does not spin. This particular galaxy is among the most massive in the early universe, containing several times as many stars as our own Milky Way. Yet it does not exhibit the rotation that we see in nearly every other galaxy we have ever observed. Rotation is fundamental to galaxy formation. Gas collapses, it spins up from conservation of angular momentum, and it forms a rotating disk. Without rotation, galaxies should be amorphous and disorganized. Yet this galaxy sits in the early universe like a cosmic fossil, a relic from a time when galaxies should have been chaotic, turbulent, and still actively forming. Instead, this galaxy is dead. It is no longer forming new stars. It is not gathering new material. It is just sitting there, impossibly massive and impossibly ancient, a monument to stellar processes we do not understand. Scientists at Texas A&M University made another shocking discovery. They identified a tight cluster of at least 5 galaxies caught in collision with one another, all occurring approximately 800 million years after the Big Bang. Galaxy mergers are violent events. They reshape stellar systems and distribute matter across vast distances. To see 5 galaxies simultaneously merging in the early universe suggests that galaxies were far more interactive and mature than our models predicted they could be. And these discoveries just kept coming, month after month, each one adding another brick to the growing wall of evidence that something was fundamentally wrong with our understanding of how the universe works. The pattern became undeniable. The early universe should have been a chaotic mess of formation and turbulence. Instead, JWST was revealing galaxies that were massive, structured, organized, and mature. Meanwhile, in another area of research, JWST was making equally disturbing discoveries about the chemistry of space itself. Scientists discovered complex organic molecules frozen in ice around a young star in a neighboring galaxy called a nearby galaxy, cloaked in thick clouds of gas and dust. These molecules included benzene, methane, and even the highly reactive methyl radical. The methyl radical is particularly significant because it is extremely unstable. On Earth, it exists for only fractions of a second before bonding with other atoms. Yet JWST detected it frozen in ice in deep space. This was the first time any of these molecules had been detected outside the Milky Way. The research team, led by the Center for Astrobiology in Spain, found an extraordinary concentration of these organic molecules in a region that should not contain them. How were these complex carbon-based compounds forming in the early universe when the chemical precursors for their creation should not have existed yet? The conventional understanding has always been that complex chemistry requires time and multiple generations of stars. The earliest stars should have been made of only hydrogen and helium, the primordial elements created in the Big Bang itself. These stars should have been chemically simple and should have formed chemically simple objects. Over time, as stars died and exploded, they would create heavier elements like carbon, oxygen, nitrogen, and iron. These elements would seed new regions of space with more complex chemical precursors. Then, new stars would form from this enriched material, and around these new stars, complex molecules could gradually build up. But JWST was finding this complex chemistry far earlier than should be possible, in regions where only primitive materials should exist. This represents a fundamental challenge to our understanding of chemical evolution in space. Then came a discovery that shifted the entire conversation toward the possibility of life itself. In April 2025, a team of astronomers using JWST detected something extraordinary in the atmosphere of a distant exoplanet called K2-18b. The planet orbits a red dwarf star approximately 124 light-years from Earth, in the constellation Leo. It is a super-Earth, or mini-Neptune, with a radius 2.6 times larger than Earth's and a mass about 8.6 times greater. It sits in what is called the habitable zone, sometimes known as the Goldilocks zone, the region around a star where liquid water could theoretically exist on a planet's surface. But what made this discovery shocking was the specific molecule detected in the planet's atmosphere by the research team led by the University of Cambridge. The researchers claim to have found dimethyl sulfide, or DMS. On Earth, dimethyl sulfide is produced almost exclusively by marine life. Specifically, it is created by organisms living in the ocean, particularly phytoplankton and algae. When these microscopic creatures are consumed by marine animals, the digestion process releases dimethyl sulfide gas, which escapes into the atmosphere. The gas is volatile, rising upward and eventually dispersing into the upper atmosphere where it can be detected by sensitive instruments. It is a biological marker, a chemical fingerprint of life itself. On Earth, if you detect DMS, you are detecting the presence of living organisms. If the detection was real, if scientists had truly identified this molecule in an alien planet's atmosphere, it would represent the most significant discovery in human history. It would be direct evidence that life exists beyond Earth, that biology emerges wherever conditions allow it to flourish. The implications would reshape philosophy, religion, and our entire understanding of humanity's place in the cosmos. News of the discovery spread rapidly through scientific channels and into mainstream media. But the excitement was short-lived. Within months, other researchers began questioning the detection with increasing urgency. They reanalyzed the data and proposed an alternative explanation. The spectral signals attributed to dimethyl sulfide could just as easily belong to ethane, a common hydrocarbon found in the atmospheres of planets like Neptune. Ethane is not associated with life. It is just mundane chemistry, the product of routine chemical reactions that occur in planetary atmospheres everywhere. The problem is that both molecules produce similar spectral signatures at the infrared wavelengths, where JWST observes. They are molecular twins in terms of their spectroscopic properties. When one team found the biosignature signal, they had looked at the data in a specific way, binning the information into particular frequency ranges. They had made choices about how to organize the data, which ranges to emphasize and which to downplay. But when other scientists reanalyzed the same raw data using different binning methods, the apparent dimethyl sulfide signature vanished. Instead, they found evidence of ethane and other common compounds. The promised evidence of alien life collapsed under scrutiny from the scientific community. This pattern began to emerge across multiple JWST observations. The telescope would reveal something extraordinary, scientists would announce a breakthrough, and then peer review would reveal complications, contradictions, and alternative explanations that cast doubt on the original claims. It is a humbling reminder that even our most advanced instruments are limited in what they can tell us, and that human interpretation of data always involves choices and assumptions. The dimethyl sulfide detection has become one of the most contentious claims in contemporary astronomy, with researchers remaining deeply divided over whether the signal is real, whether it represents life, or whether it is simply an artifact of how the data was analyzed and processed. Teams have published multiple peer-reviewed papers taking contradictory positions, and the controversy shows no signs of resolution. Yet, even amid the controversies and the disputes over interpretation, the fundamental discoveries about the early universe remained undeniably true and irrefutable. The early galaxies are there. They have been photographed and measured multiple times by different instruments and different research teams. Their existence cannot be disputed, only explained. And the problem is that the current explanations do not work. Our models cannot account for what we are seeing, no matter how we adjust the parameters or refine the calculations. Some physicists have begun proposing more radical solutions that challenge the very foundations of modern cosmology. Perhaps the universe is older than 13.8 billion years. Perhaps our calculations of cosmic expansion have been systematically wrong, and the universe has been expanding at different rates than we estimated. Perhaps the Big Bang did not happen the way we think it did, or perhaps there was no Big Bang at all in the conventional sense. Perhaps our entire framework for understanding cosmic origins is fundamentally mistaken. These ideas are deeply controversial, challenging decades of research and mathematical frameworks that have been tested against countless observations and experiments. But when faced with evidence that contradicts those frameworks, scientists must consider even radical alternatives. This is how science advances. Other researchers have proposed that the early universe operated according to different physical laws than those we observe today. Perhaps in those first few 100 million years, when density and temperature were extreme, reaching levels far beyond anything we can recreate in our laboratories, particles and forces behaved in a way that cannot occur in our current, cooler universe. Perhaps the physics we know breaks down in those extreme early conditions, and we need entirely new theories to explain what was happening. Perhaps quantum effects that we dismiss as negligible in the modern universe played crucial roles in the early universe's evolution. There is also the possibility that our understanding of dark matter is fundamentally incomplete and requires revolutionary revision. We know dark matter exists because we can see its gravitational effects on visible matter and light, but we do not know what it is or how it behaves. We have never detected a single dark matter particle directly. Perhaps dark matter was far more efficient at creating the gravitational conditions necessary for galaxy formation than our current models suggest. Perhaps there's a mechanism we have not yet discovered that allows matter to collapse and organize far more rapidly than our calculations predict. Perhaps dark matter can interact with ordinary matter in ways we have not accounted for in our models. The implications of these JWST discoveries extend far beyond abstract cosmology and theoretical physics. If our understanding of the early universe is wrong, then our understanding of how galaxies form and evolve is fundamentally compromised. This affects our models of stellar evolution, our calculations of planetary systems, and our estimates of how common habitable worlds might be. It means that the building blocks of life could be far more common than we thought, or far less common, depending on how the physics works out. It means we may have been systematically overestimating or underestimating the probability of life emerging in the universe. The discoveries also raise profound philosophical questions about the nature of knowledge and human understanding. For centuries, science has progressed by building models, making predictions based on those models, and testing those predictions against observation. This process has been incredibly successful. We have sent robots to Mars and beyond, split the atom and discovered its structure, mapped the human genome and understood the genetic basis of heredity, and created technologies that previous generations would have considered magic or impossible. We trust this process because it works. It has given us antibiotics and electricity, computers and space travel. But the James Webb Space Telescope is revealing that one of our most fundamental models, the model of cosmic evolution itself and how the universe expanded and evolved, may be wrong. This does not mean that science has failed, quite the opposite. Science has succeeded in its primary mission, which is to reveal the truth about reality even when that truth contradicts our expectations and upsets our comfortable assumptions. The failure was not in the scientific process, but in our initial assumptions about how the universe works. Science has done exactly what it is supposed to do. It has found reality to be different from our predictions. What makes these discoveries particularly unsettling is that they were not supposed to happen. The James Webb Space Telescope was built with explicit expectations based on decades of cosmological research. It was supposed to confirm our existing models with greater precision and tighter accuracy. It was supposed to find the earliest galaxies and observe them reaching specific milestones at predicted times according to our calculations. We expected to see galaxies that were smaller, simpler, and younger than the massive, mature structures we eventually found. Instead, JWST found galaxies that had already reached those milestones long before the theory said they should have. It was as if we sent an explorer to investigate what we thought was a young forest, only to discover that the forest is already ancient, with massive trees that predate our entire understanding of how forests form. It is as if a time traveler went back to witness the birth of the universe and returned saying, "Everything is different from what you calculated. The timeline is all wrong. The chemistry is all wrong. The galaxies are already here, already formed, already dead, when they should not even exist yet." And then the time traveler disappeared, leaving behind only photographic evidence and spectroscopic data that cannot be dismissed or ignored by the scientific community. The evidence is real, the measurements are valid, only the interpretation remains uncertain. The scientific community remains deeply divided on how to respond to these challenges to fundamental theory. Some astronomers are convinced that the answer lies in improving our models of early star formation and galaxy assembly. They argue that we have underestimated how efficiently stars and galaxies could form when the universe was young, dense, and filled with the primordial material from the Big Bang. They point out that our models are based on calculations and computer simulations that make many simplifying assumptions about complex physical processes. If early star formation was far more efficient than we calculated, perhaps because of mechanisms we have not properly accounted for, then perhaps these ancient galaxies are not as impossible as they seem. Perhaps they represent the extreme edge of what is possible under our current physical laws, rather than a complete violation of those laws. Other scientists are more pessimistic about the prospects of saving current theories with minor adjustments. They argue that no amount of tweaking existing models will be sufficient to explain what we are seeing. The problem is not a matter of degree, but of kind. It is not simply that our numbers are off by a factor of 2 or 3. The early universe appears to be fundamentally different from what theory predicts. This means we need new physics, new principles, new mathematical frameworks to explain what we are observing. We may need to completely rethink our understanding of how the universe works. And there is a third camp that is carefully collecting data and avoiding premature conclusions. These scientists acknowledge that something is wrong with our models, but they are not ready to propose radical solutions without more evidence. They are calling for additional observations, more detailed measurements, and more rigorous analysis. They want to be absolutely certain that we are not making mistakes in how we interpret the data before we overturn the framework that has guided cosmology for decades. What is certain is that the age of certainty in cosmology is over. For the past few decades, astronomers have operated with a generally agreed upon model of cosmic evolution. There were debates and refinements, but the basic framework seemed solid. That framework has now been shattered by observations from the James Webb Space Telescope. The discoveries continue to accumulate. In May 2026, JWST revealed a gas giant exoplanet about the size of Saturn orbiting a distant star, but with atmospheric temperatures surprisingly similar to Earth's. This temperate gas giant exists in a configuration that contradicts our models of how planetary systems form. The planet should not be there, or if it is there, its atmosphere should be vastly different from what we observe. Another discovery revealed a planet where rocky mineral clouds gather every morning and vanish every evening. On this world, called WASP 94AB, the daily weather cycle is so extreme and so perfectly consistent that it appears almost artificial. Scientists study this phenomenon to understand atmospheric dynamics on alien worlds, but the very existence of such extreme daily variations challenges our models of planetary atmospheres. With each new discovery, the picture becomes clearer and simultaneously more confusing. The universe is not behaving the way our models predict. Galaxies are forming too fast, appearing too early, and appearing too massive. Chemical compounds are becoming too complex too soon. Planets are forming in configurations we did not think were possible. And somewhere at the intersection of all these contradictions lies a fundamental truth about how reality actually works, a truth that we have not yet grasped. The question that haunts the scientific community now is simple but profound. What are we missing? What is so obvious that we have overlooked it? What assumption have we made that is so basic, so fundamental, that we have never thought to question it? Because somewhere in the answer to these questions lies the key to understanding not just the early universe, but the universe as we know it today. The James Webb Space Telescope was designed to answer questions about the universe's origin and evolution. In many ways, it has succeeded beyond expectations. But the answers it has provided are not the ones we were looking for. Instead of confirming our models, it has torn them apart. Instead of revealing a universe that conforms to our predictions, it has revealed a universe that mocks our assumptions and invites us to think larger, deeper, and more radically about how reality works. Scientists are not panicking in the traditional sense. They are not afraid. Rather, they are experiencing the exhilaration that comes with encountering genuine mystery, the kind of mystery that cannot be solved with incremental improvements to existing theories. This is the moment when science advances by leaps rather than steps, when paradigms shift, and when humanity must revise its fundamental understanding of reality. The discoveries made by the James Webb Space Telescope in 2025 and 2026 represent a threshold moment in human knowledge. On one side of that threshold is the comfortable certainty of our models. On the other side is a universe far stranger and more complex than we imagined. The question is no longer whether we will cross that threshold. We already have. The only question remaining is what we will find on the other side, and how we will integrate those discoveries into a new, more accurate understanding of how the universe actually works. As we look up at the night sky, billions of light years of ancient starlight washing over us, we are looking at evidence of something far more extraordinary than we ever imagined. We are looking at the remains of a cosmic history that unfolded according to rules we do not yet understand. We are seeing the fingerprints of physics that operates in ways we have not yet described, and the most powerful telescope humanity has ever built is just beginning to decode what those fingerprints mean. The mystery deepens with each observation. The questions multiply with each discovery. And somewhere in the data streaming back from the James Webb Space Telescope, somewhere in those infrared photons that have traveled for billions of years to reach our instruments, lies the answer to perhaps the most important question of all. How does the universe really work? And when we finally answer that question, everything we think we know about reality will have to be reimagined.